All right, looking now at that galaxy cluster, I said that the mass that you get in the galaxies themselves are actually a pretty small fraction of the entire mass. And one major component is what you see in blue, and I described on the first slide, which is X-ray emission from a very hot gas, which is known as the intracluster medium. Now that gas is mostly ionized hydrogen, which means that there are free electrons and free protons, basically, ionized hydrogen. And since the electron mass is much less than the proton mass, then we can get an approximate number of the, or scale at least, the total mass in terms of those two components. So what we could say would be that the total mass would be given by the number of adding up both protons and electrons. So m is basically the average mass. And now what we're going to say is that since the electron mass is much smaller, over 1,000 times smaller than the proton mass, then we can approximate all of the mass being in the protons. And if there are half of the total number n is in protons, then n over 2 is the number of protons, and they have a mass of mh, where again we're approximating that the mass of ionized hydrogen is roughly the same as hydrogen 1. So that's fine. What we can do actually is use the definition of the thermal kinetic energy and our measurements of the motion of the galaxies, where we already saw that the average kinetic energy was 3/2 m sigma squared. All right. And here, however, what we're going to look at is that the gas particles also have a very similar velocity to the galaxies themselves. And this is some type of equilibrium where we're saying that on average, these gas particles can, if they're colliding, say, with the galaxies or with each other, and they're over these distances, the random motion will give you the same sigma squared as it would for the galaxies that you can measure easily. So in this case now, this average kinetic energy is not for a galaxy, but it's actually for a particle that has an average mass of little m. And that's useful because the thermal kinetic energy of particles moving around is 3/2 kT, where k is the Boltzmann constant, and so that should be a little k, and big T is the temperature of the gas. So we can calculate that 3/2 m sigma squared, and what we'll do is we could of course substitute n, that this m here is actually 1/2 mh, as we saw from the equation above. And using our sigma squared of about 1,000 kilometers per second, this gives us a temperature that is about 10 million Kelvin, or 10 to the 7 Kelvin, which is a very hot temperature. and gives off its emission in the X-ray energy for the thermal. So you think about this thermal blackbody spectrum that we had before when we looked at stars, but now it's shifted up to very short wavelengths or high energies and gives you this X-ray emission that you see as the blue gas. All right. Now, there's also a way that you can measure the mass of that gas, and you'll see that it is about 10 times more massive than what you get from the galaxies. So you have about 10 times more mass in that diffuse intracluster medium than you do in the galaxies themselves. Finally, we're going to look at another way of getting the total mass of a galaxy cluster, and that is gravitational lensing, which is a pretty cool application of general relativity, where we have the curvature of space-time. And you see on the bottom left, there's this amazing image where you've got this blue, almost complete circle, a ring, and it's a smeared out image of a blue galaxy. And that blue galaxy, from our point of view from Earth, is actually located behind that central large orange elliptical galaxy. So it should actually be hidden from our view, but in fact it's spread out in a ring over quite a large angular space. And what's happening is shown in the diagram to the right, which is that we can think about that blue galaxy as the point S on the left of the diagram, the central large elliptical galaxy is this black dot, and then on the right of the diagram is meant to be an eyeball, which is our observation point on Earth. So again, you can see that this blue galaxy was behind this large elliptical galaxy. And the idea is that that massive elliptical galaxy is bending space-time around it. And that means that instead of following a straight line in space, the light actually follows this bent path, and it has an angle over which it bends. So this then gives you the diagram where we have light going to the upper right and then bending around and then reaching the observer. Now for us, we trace light back in a straight direction. So when we see that light, we form an image. The image, which is labeled as I, is along that straight line, which is not where the blue galaxy is located. It is actually tracing out this ring. And there is symmetry here, so that the curvature is the same in a circular path, and that means that we should then, if it's directly behind it, as shown in the diagram, trace out a ring. Now, for the problem class, we left it up to you to use this diagram and use geometrical arguments to actually derive a useful formula for how you can calculate that angle shown, theta e, which is known as the Einstein angle. You can calculate that using geometry if you know the angle alpha. And alpha is given from general relativity, so that's far beyond the scope of this module. So I'll just write down what this alpha, known as the bending angle, is. And that is given by the gravitational constant g times the total mass of that object that's bending the space-time, divided by b, divided by c squared, and multiplied by 4. Now B is shown in the diagram, and this is called the impact parameter, and it is related to that distance over which the light traveled when it was being bent and then bent around towards the observer. And this is where geometry comes in, because you want to relate that B in terms of things that you can measure, which are shown as the distances from the observer to that central object, that black dot, DOL, and also that distance from the black dot to this galaxy behind it, which is S, DLS. So you can also, adding up those, you get the total distance, which is DOS. All right, so again, in the problem class and on a video that Giuseppe's created, he shows you get theta E, the Einstein angle, is the square root of 4gm over c squared times dLs divided by dOL DOS. Okay. So this is really useful because, as I said, if we can measure those distances and we see from the image gives us the angle theta E from the ring and from that central object, then we can just rearrange this equation and solve for m. So all you're doing is rearranging, and you get the mass of that object is this measured theta E squared times c squared, which is the speed of light squared, times DOL times DOS divided by 4g dLs. Okay. Now, in this example, this object that was bending space-time is an elliptical galaxy, but often it's entire galaxy clusters that are doing the bending because they are extremely massive objects. And the way then to get this mass is just to use this gravitational lensing. I should also say that this is a quite rare occurrence of the background light source, this blue galaxy, being directly behind it. If it's off at an angle, then it's not a perfect ring, and it might appear more as two images. So you don't always see such perfect rings, Einstein rings, but in this example, you do. And the mass that you get, if it is a cluster, a galaxy cluster, it agrees with what you would get from the velocity dispersion. And once again, the story is that even when you include the intercluster medium, the gas, you still don't have enough mass that you can see in the gas and in the galaxy